Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 22. A total charge Q is distributed uniformly throughout a sphere of radius r equal to 12 centimeters. If the charge density is given by ρ equal to 4.7 millicoulombs per meter cube, find the total charge Q. The volume charge density ρ is equal to dq over dv, where dq is the infinitesimal charge in the infinitesimal volume dv, from which we can write dq equals ρ times dv. If we take the integral of both sides, we say that integral of dq is the total charge capital Q, and since ρ is constant, it can be taken outside the integral sign. Therefore, we obtain Q equals ρ times integral of dv. By the same way, integral of dv is the total volume of the sphere. Then we obtain Q equals ρ times v. Since the volume of the sphere is 4 pi over 3 r cubed, then we can write 4 over 3 times pi times ρ times r cubed. Now we substitute the numerical values into this formula. As a result, we obtain the total charge as approximately 3.40 times 10 to negative 5 coulombs, or 34 microcoulombs. Okay, let's solve part B. A total charge Q is distributed non-uniformly throughout a sphere of radius r, which is 12 centimeters. If the charge density is given by ρ equals A times r, where r is in meters and A is 4.7 millicoulombs per meter to the fourth, find the total charge Q. dq equals ρ times dv. We are given ρ as A times r, and dv is known as 4 pi r square dr, or simply 4 pi times A times r cubed dr. If we take the integral of both sides, the left hand side, that is the integral of dq, becomes the total charge. And on the right hand side, since 4 pi and A are constant, then we can take them outside the integral. So we are left with the integral of r cubed, and the endpoints of the integral are 0 and capital R. The integral of r cubed is r to the 4 over 4. 4's are cancelled, so the total charge is obtained as pi times A times r to the 4. Now we put the numerical values into this formula. Therefore, we obtain approximately 3.06 times 10 to negative 6 coulombs, or it is 3.06 microcoulombs. Okay, we are done. Let's solve part C. C. A total charge Q is uniformly distributed throughout a spherical shell of inner radius r1 as 8 centimeters and outer radius r2 as 12 centimeters. If the charge density ρ is 4.7 millicoulombs per meter cubed, find the total charge Q. Since the charge is uniformly distributed throughout the spherical shell, we have the volume charge density as total charge over the total volume of the spherical shell. From this, we obtain the total charge as ρ times V. The volume of the spherical shell is the difference of the volumes of the outer and inner spheres. That is 4/3 times pi times R2 cubed minus R1 cubed. Or simply Q is 4/3 times pi times ρ times R2 cubed minus R1 cubed. Now we insert the numerical values into this formula. So we obtain the total charge as approximately 2.39 times 10 to negative 5 coulombs, or 23.9 microcoulombs. Okay, this is the answer to this part. Let us solve part D. D. A total charge Q is non-uniformly distributed throughout a spherical shell of inner radius R1 being 8 cm and outer radius R2 being 12 cm. If the charge density is ρ equal to 8 times R, where R is in meters and A is 4.7 millicoulombs per meter squared, find the total charge Q. dQ is found by the formula ρ times dV. Here ρ is 8 times R and dV is 4 pi R squared dr, or simply 4 pi times 8 times R cubed dr. Now we integrate both sides. Integral of dQ is the total charge. On the right hand side, since 4 pi a is constant, it can be taken outside the integral. Then we are left with 4 pi a times integral of R cubed. The integral limits are R1 and R2. Since the charge starts at R1 and it is over at R2. Since the integral of R cubed is R to the fourth over 4, total charge is obtained as pi times a times R2 to the fourth minus R1 to the fourth. Now we put the numerical values into this formula. As a result, we obtain 2.46 times 10 to 6 coulombs, or 2.46 microcoulombs. Okay, this result brings us to the end of the discussion of this problem. Thank you for your attention. See you in the next video.